Let's explore this GMAT problem. To get the most out of this video, pause the recording now and solve the problem yourself. The correct answer is C. The words must be are a clue that I could try to solve this problem using the counterexample method I showed in another video. However, the numbers here are just too big to work with comfortably. I don't want to multiply 252 and 110, so I'm going to look for another way. The word multiple is a clue that I can use prime factors to help solve this problem. Let me show you how. I can break 252 down into its prime factors using a prime factor tree. Use the branches to divide 252 into smaller numbers until you reach a prime number. For example, if I divide 252 by 2, I get 126. And since 2 is a prime number, that's the end of that branch. Then I see that 126 is even, so I can divide by 2 again. 63 is equal to 7 times 9. 7 is a prime number, and 9 is equal to 3 times 3. Note that 1 is not a prime number, and we're not going to include that in our prime factor tree. You could think of the prime numbers as the flowers on the ends of the branches, but perhaps that's going too far. However, it is helpful to circle the prime numbers to keep track of them. 252 equals 2 times 2 times 3 times 3 times 7. I can say 252 has these prime factors. Mathematicians often describe prime numbers as the atoms that make up the molecules of larger numbers. Each integer is composed of a unique group of prime numbers multiplied together. In other words, every integer greater than 1 can be expressed uniquely as the product of prime numbers. And this can help us solve certain problems. If I know that 252 has these prime factors, I can say that any multiple of 252 also contains these prime factors. A multiple of 252 may contain some more prime factors as well, but it will definitely contain these ones. What about y? Go ahead and repeat that prime factor tree approach with y if you haven't already. Perhaps pause the video. Y has prime factors 2, 5, and 11. The next step is to realize that if I multiply x and y together, I combine all the prime factors of x and y, including repetitions. The prime factor tree for x, y could start off with branches for x and y, going down to all the prime factors of x and all the prime factors of y. I can say that x, y definitely has these prime factors. I can use this fact to assess the 3 mini questions. For xy to be a multiple of 77, it must contain the prime factors of 77, which are 7 and 11. Does xy contain these prime factors? Yes. For xy to be a multiple of 16, it must contain the prime factors of 16. That's 2 times 2 times 2 times 2. I can see that xy has 3 2's in its prime factors, but what about the fourth? We don't know. Xy might not be a multiple of 16. As for 45, that equals 3 times 3 times 5. Does xy contain these prime factors? Yes, it does. The correct answer is C. To review, notice how we translated our facts and questions into facts and questions about prime factors, making the problem easier to solve. I call this process thinking in prime factors. We ended up saying things like, does xy contain a 7 and an 11? This is too good to stop here. Let's do another problem. Pause the video and solve this one yourself. The correct answer is E. I gave you a hint that prime factors might be useful here. Let's break 3,150 down into its prime factors. Notice, I'm free to take the easiest path when I write out my prime factor tree. I don't have to divide 3,150 by 2. It's easier to use 315, and 10. If I divide 10, I get 2 and 5. As for 315, I can see it's a multiple of 5, so I'll work out the next branches are 63 and 5. 63 is 7 times 9, 7 is a prime number, and 9 is 3 times 3. So 3150 has the prime factors 2, 3, 3, 5, 5, 7. Next, there's a piece of information that we haven't used. 3150 multiplied by y is the square of an integer. Let's think for a moment about the prime factors of perfect squares. As always, taking some examples will help us. 36 is equal to 6 times 6 and has the prime factors 2, 3, 2, 3. 64 is 8 times 8, so it has 6 2's in its prime factors. Notice the symmetry of these prime factor trees. Here's a rule about perfect squares. They have prime factors that can be split into 2 equal groups. That makes sense because a perfect square is 2 equal numbers multiplied together. In other words, the prime factors of square numbers are in pairs. Let's use this fact to help us finish the problem. Looking at the prime factors of 3150, I can see it has a pair of 5's and a pair of 3's. But it has only one 2 and only one 7. So to be the square of an integer, it needs to get an extra 2 and an extra 7. Where will it get them from? They must be provided by y. Therefore, y must be 2 times 7, that's 14. Here's another example of thinking in prime factors. Check out the link below for a follow-up task.